Okay, so this is now being recorded. That way, I'll post this at YouTube. So for anyone watching this later on, should be good. So this is a pretty difficult week. I kind of have a different thing than normal. So normally I just kind of go through the PowerPoint, but this one's going to be a little more, it's a pretty short PowerPoint, just because it's mostly not, it's more or less like dealing with actual like calculations of things, and it's not as much talking. So if you like the math side of this class, this week will be kind of interesting. You'll probably like it more. I would say this week, more or less, it's like a almost like a puzzle piece. That's kind of what I would relate this week to. So if you like puzzles, you might like what we're doing this week. Okay, so right now you should see my PowerPoint on rheostats and potentiometers. So that's basically what this week is. I'm going to give a quick overview of what a rheostat / potentiometer is, and then I'm going to kind of basically explain why we're talking about it and go through the logistics of this week. So view, okay. So to begin, basically a rheostat is this little picture on the right here. I always try to add a picture just because I think it's nice to kind of visualize what we're talking about. But basically, when talking about circuits, in some situations, there might be times where you need or want to restrict the current for given reasons. And we'll talk about these reasons in a minute. But basically, that's the point of a rheostat. So a rheostat, which is ultimately just a type of variable resistor or a resistor, is able to control and adjust how much current is flowing through a circuit. And it does this by manually changing resistance. So the term rheostat actually comes from the phrase changing stream. So stream in this case is current. So that's kind of what it does, is it changes the current in various different times throughout a circuit. So basically it's a range of resistors. So a rheostat is a range in the sense that we're not like just having one current the whole time. It's kind of giving us like a range that we can have a current that's this speed at this time, or it might be this speed. And below that, I think this is the best example. So think of a dimming switch. This is a perfect example of real life situations where a rheostat is used. So a dimming switch is one of those ones where you like you can dim the light by it's probably just like a level kind of thing, and the more you push it up, the brighter your light goes. So that way, they have those in houses sometimes, like if you don't want full light, you can have like a dim and you can adjust the lighting. So this is an example of when we have a rheostat. So in a regular circuit in classes, when you do examples of actually creating a circuit, typically just a series circuit, you normally have one light bulb in that circuit, and that's your load. And as soon as our circuit is complete, that load lights, indicating that those electrons are flowing. However, the load lighting, or the light bulb lighting, is lighting because current's going through it. But the more current we push through that light, or the more electrons that are getting pushed through into that load, the brighter it's going to light. So if at one point in time we're pushing 20 amps into that load, which again, the load is just a piece in your circuit, like a light bulb or any type of electrical equipment that you're trying to turn on. So if we're pushing a ton of amps, 20 amps into that light bulb, and it lights really bright, and then we have a rheostat, this rheostat is going to be able to adjust that current maybe down to 5 amps. So then all of a sudden our light is going to dim because less electrons are getting pushed through it. So basically that's just the point of a rheostat. So it allows us to control current, which is useful for situations in which we're using electrical components like a light bulb or like a motor, and we're not always wanting the same exact outcome. So the rheostat changes ultimately the outcome. So it changes how our electronics or electricity is working for us. So basically that's why we're talking about a rheostat. Just some main things to know about this. So basically just that it controls how much current is flowing. So know that that's important. And then know of the different examples. So like a dimming switch is the most significant example of a rheostat, but you might have things like a motor, or just the fact that it's a smooth range. So, you know, like those dimming switches, the higher, the more you push up the like level, the brighter it's going to get. So just that's main ideas to remember for this. So bringing up this again, basically the main reason that I'm bringing up this again is because the equivalent resistance is coming back, and this time it gets a little more complicated yet again. So we talked about a series circuit, how to calculate equivalent resistance. We talked about a parallel circuit, how to calculate equivalent resistance. These equations right here at the bottom. These are important. Basically what this week does is it shows us that in real world situations, we very rarely have just a series circuit or we have just a parallel circuit. Typically we have both. And we are basically going to learn how to calculate total resistance or equivalent resistance, total current, and total voltage, given situations where we have a combination circuit. And a combination circuit is just one that is both a series and a parallel circuit. If that doesn't make sense, it will in a minute. On the right here, I did add one note. This is really, really, really important for this week. And it's the fact that when you are calculating equivalent resistance for a parallel circuit, there is another way to write the equation. So this is the way that I was explaining to you guys. And it was when we did 1 divided by the fraction, and then you did 1 over that fraction, you added them all together. Hopefully you remember that from last week. This is an easier way to do the calculation. So if you only have 2 resistors in a circuit, I would recommend calculating total resistance this way. If you multiply both of the resistance together and then divide that total by the sum of those resistors, you will also get your total resistance. So this right here, same equation that we were doing in the past, it's just an easier way to write it. So I would remember this. It's very, very important for this week. And this is the equation that I would use again when you have 2 resistors. Perfect example is right here. In this situation, we have an R1 of 10 and an R2 of 10. So we have a resistance of 10 ohms and a resistance of 10 ohms. Multiply them both 10 times 10 and then divide by 10 plus 10. 10 times 10 is 100. 10 plus 10 is 20, 100 divided by 25. So the answer here is just 5 ohms. So that's the total resistance. So it's that easy. And you could use this whole equation too, and you'd get 5 ohms too, but definitely this equation is easier. For this week, you're going to have to calculate total resistance a lot of times. So this equation is going to become very useful. Okay. So this is where this class can get challenging. So hopefully you can bear with me. And then, you know, obviously anyone watching this, if you have questions, let me know and we will work through it, because if you don't understand this, it can get frustrating and confusing, and we don't want that. So this is an example of an exact problem that was done in the YouTube videos this week, which are very helpful and very great. But I think it maybe is good to look at it again, break down the components. I have this all typed up because I think it's easier to understand. And then obviously I just think this might be better. We redo the same equation or problem, and so you can see all the different components of it and why it works, because it's basically the same process this week for every single circuit. You just have to understand the practicality or the like reasoning behind what we're doing, or it's going to be confusing. So in this situation, this is right here, this main piece. Don't look at this for now. You can ignore this little box, this red arrow, and this for now. Just look at this. So this is a combination circuit. And the reason it's a combination circuit is because it's a combination of a series and a parallel. Your series circuit is right here. This is a series circuit. If you ignored all of this that was over here, you would just have a series circuit. If you just had this first rectangle, you just have a series circuit. Where this gets hard is right here. So this is a junction or a node. And at this junction, we have electrons going this way and we have electrons going this way. So this circuit all of a sudden becomes a parallel circuit. So this is, again, a combination circuit because we have a combination of a series and a parallel circuit. There's a couple things that I think are important to note here. And it's the fact that right here, this is not an example of a parallel situation because our electrons are still flowing in one direction. They're still going like this. All the electrons are going like that. This is an example of a parallel situation because when the electrons that are flowing from here stop right here, they split up. Some are going to go this way and some are going to go this way. So that's basically a huge distinguisher and something that you need to know for when calculating total resistance and all the different components you want to calculate. So again, the parallel situations, the parallel resistors that we are concerned about are the ones that at a node, which a node is just a point of branches, you have electrons going multiple directions. We do not have electrons going multiple directions, only going one here. We do right here. We do not have multiple directions right here or right here, but again, we do here because we have electrons coming this way and we have electrons coming this way, and then all the electrons meet up here. So basically what we're calculating for this problem is we're calculating what our total voltage is, our total resistance, and our total current. So in combination circuits and for this week, you're going to be asked to calculate the same things we've been having to calculate in previous weeks. However, there adds a different layer to it that can be very difficult. And hopefully I can explain this layer in a way that makes sense. So the first thing here is in the videos they talk about in situations where you have parallel resistors or parallel circuits, or they call it parallel resistors right here. These are the parallel resistors because they're in this parallel situation with these. When you have situations like this where in a combination circuit you have a parallel resistors, you should always try to first calculate these together, calculate your total resistance by basically treating this as its own parallel circuit, and then you can add that back up to this series circuit. So I'll explain this in better terms when going over this. So we already know by looking at this equation right here that in order to calculate total resistance in parallel, that you can use this equation, R1 times R2 plus over R1 plus R2. So that's why they did this right here. And that's why in the YouTube videos, that's why they did this. So it's because they're looking at this 10 ohms and they're looking at this 10 ohms. And they're looking at this and they're calculating it like this and not just adding them together because this is a parallel situation because we have electrons going this way and we have electrons going this way and this way. So that is why. So again, first step here is they are calculating the total resistance for this parallel side of this combination. So they're totally ignoring this side and they're only working and dealing with the parallel situation. Once they decided that this was 5 ohms, which again is just using this equation, they rewrote the circuit. So it looks like this. So now we have 10 ohms here and 5 ohms because this 5 ohms here is the sum of the resistance or the total resistance of these two, right? So 5 ohms and 10 ohms. We already know that the total voltage is 10. So this is called an equivalent circuit, and this equivalent circuit basically means that we simplified a combination circuit to look like a series circuit in order to make it easier to calculate different constituents or different parts of the problem like total voltage, total resistance. And that's because having a series circuit is way easier when you can just use this equation. So all we did with this part and all we did using this equation was find this 5 ohms so we could rewrite this circuit right here in an equivalent circuit so it's easier to understand. So this is what we did here. So the same thing as this, just again, this 5 comes from the parallel circuit here, and this 10 comes from this 10. This 10 volts here, we know because the total voltage remains the same regardless. So that's easy. You're typically normally given the total voltage. So on this left side here, these are the things you're typically going to be asked yourself for. That is the total voltage, the total resistance, the total current, junction currents. Junction currents are right here, and voltage drops. Junction currents we talked about again last week when we talked about how when that current splits up, we have electrons going this way and electrons going this way, but the sum when they add back up together must be the same as whatever the current was here. So the current, like let's say if the current going into this junction is 10 ohms and we have 10 amps and we have 6 amps going here, we know that we have 4 amps going right here because it has to sum this, because then when they meet back up here, we have the 6 and the 4, so it can equal 10, and then we have 10 amps, which is what we started with. Same thing with voltage drops. Whatever the voltage drop is here, right on this line, whatever the voltage drop is here, it splits up right here, and then it should sum back together right here. So back to this problem. Once you have this, this is the easy part. So now we can just calculate everything like normal. So for example, the total resistance now is just the sum of both of these. So just 10 plus 15 to get 15 ohms. And we know that because of Ohm's law, or not Ohm's law. We know that because of this equation here, we can just add them together. So that's how, in the YouTube video, that's how they got 15. They just added both of these together. For the total current, the way that we got that is just using Ohm's law, because we know when we have a series circuit, we can use Ohm's law, which is just V equals I times R, or V over R equals I. So V 10 divided by 15 is 0.667. So that is exactly how they got that number there. So basically, this is how they solved for all of the different components here. The last thing that can be kind of tricky is this voltage drop that they calculated. So the way that they got the voltage drop right here to be 6.66, I think it might be easier to, I don't have it up anymore. I thought I had the YouTube video up still. But the way that they got this 6.666 is they know that the total current is 0.6667. If we put that into this situation right here, which I'm going to grab a calculator, maybe. Sorry, just give me one moment. Get a calculator. 7. So if you do 0.6667 times 10, again, 0.667 is your current. So if you did 0.6667 times 10, which is your resistance, you're going to get 6.667, which means that this 10 ohm, your voltage drop right here is 6.667. Because your voltage drop at any given location, you can calculate by just still using Ohm's law. V equals I times R. But in this case, when we want the voltage drop at just the 10 ohms, we're only going to use 10 ohms as our R, not 15. So to find a voltage drop in a specific resistor, you just take that resistance at that time times the total current. So again, 10 times 0.667 is 6.66. Total voltage means that right here is 6.66. This is where it gets a little bit confusing. So the voltage drop again right here is 6.66. I wonder if I can break that actually. So it's easier. Let's write that. Which if you look in the video, he does write that. I can't. But so let's have a thing here. So 6.67 is the voltage drop for this line right here. And let's put it above this 10 ohms so we know that we're talking about that. So we can also calculate the voltage drop for this situation, for this parallel situation of the circuit. So the way that we calculate voltage drop for this situation is using the 5. Because remember, the 5 again is the total resistance for this parallel part of the circuit. So 10, we use this equation and got 5. So if you did 0.667 times 5, you'd get 3.33. So that means, and since this is 5 and these are the same, that means that both of these are 3.33, which makes sense. Because if this is 0.333 or 3.33 and this is 3.33, that means when they meet back up here, it's going to add again to 6.67. 6.67 is exactly what we had the voltage drop here, which is right here. So that means that we're all right. Plus, the other thing to note too is that the 6.67 plus the 3.3 here is going to equal 10, which makes sense because we know that that's something that we learned. And the voltage drops, or the sum of the voltage drops, always equals the total voltage at the end, and it does if this is 3.3 and we treat it as a series. So again, this is basically what you have to do for this week, and it's using different combinations of what we did the past couple weeks to calculate different things in a combination circuit. So to kind of skim over again what I just did, I first, you'd want to write down total voltage, which you're normally given, which is whatever your battery is there. You need to find your total resistance, your total current, your junction currents, which we didn't found, but you do the same way using V equals IR, and then using your ohms here, and your 10 volts here. And then we found our voltage drops, which was, again, same thing. We just used these to calculate voltage drops. We knew that the split happened and it has to set together. So these are the things that you're going to ask to solve for, and these are the type of situations you're going to get. So you're going to get situations where you're going to have to first calculate the parallel resistance, given the two different resistors you have in the combination circuit, then sum those together with the series part of the circuit to find different variables. So the only other two things I wanted to mention here, I know this is kind of a short week, but I think that hopefully this is helpful. And then if there's questions, obviously I will meet with anyone individually. So this is for the quiz this week. You have to look at both of these two. And I just wanted to touch by both of these because there's a couple things that I think are worth noting. This situation is the same exact situation that we just did here. And this is what I mean. So in this situation, it's actually easier. So you are asked to solve, let's say in this situation, this is a series parallel combination circuit. So it's a combination again, and these are where you have parallel situations in the circuit. So this is where this comes important. Right here, this is a junction or a node, and that is because some of our electrons go this way and some of them go this way. So that means R1 and R2 is an example of a parallel resistor. So this is a question, I think. So and just recognize that the reason that this is a parallel resistor is because we have electrons splitting up. On the contrary, you might have a question that has you look at the second graph, and it might say, are R2 and R3 parallel or series resistors? And a lot of people look at this and just want to say parallel because it looks like there's a lot of lines going. But this is actually only a series. So R2 and R3, there's no junction in between these right here that's splitting them up. So nothing between R2 and R3 is splitting up those electrons. So this is an example right here of a series situation. So again, a situation where we're going to have a series resistors. Situations like R2 and R4 is an example of a parallel situation, because at this node right here, or this junction, we have electrons going this way and we have electrons going this way. So that's basically a big thing to note for this week and a lot of the quizzes. So I know a couple of questions to ask you about that, and it gives you two different resistors looking at the figure, and you'll have to figure out if they're parallel or series. So again, this one is parallel because we have a node right here and we have some electrons going this way and we have some electrons going this way. So another question that they'll probably ask you for this week is they're going to want you to calculate the total resistance again. And it's the same situation that we did here, but I'm just gonna do it. And if someone watches this, at least you'll get one of the answers on the quiz, because I think it's very helpful to see it in a different perspective. So in this situation, I'm just going to draw it out again. So if you want to draw this out with me, or at least look at the diagram again that you're given. Again, this is just like the figure 1. So on your quiz this weekend, if you haven't taken it yet, this is exactly word for word the problem that you're given. Sorry, I'm just writing it down so I don't forget what it looks like. Okay. So I'm going to draw. Okay, so I'm going to draw this exact situation that we just looked at. So it looked.
I love the fact that Joe Burrow goes 1, 2, 3, balls coming out. Look at how he's already starting to throw the football. Now we've heard all heard the phrase, well, football even in these three, folks, that's not easy. That corner is still 3 yards ahead of Jamar Chase. But this player has got so much trust that I'm going to take a chance to practice football. Now, this is so Jamar Chase is really trailing that corner 3 yards. You really know why he trusts him for practice football. In 20 yards, Jamar Chase goes 3 yards from behind the
So in this example, this is a horrible representation, but you should hopefully get the point. So basically in this situation, we have two areas where we have parallel circuits. So we have a situation here that's a parallel circuit with this 100 ohm and this 250 ohm.
Come on, this shit, Joe.
And then we have a situation right here that is a parallel resistor, because again, these junctions right here, or these nodes, is where our electrons are splitting up in two different pathways. So in order to calculate the total resistance for this situation, first you need to calculate the total resistance for the parallel situation. So the way that we do that is the same way that we did in that last problem. And first, I would take it one piece at a time. So we know that that equation that I showed you at the beginning was R1 times R2 divided by R1 plus R2. So for this first one here, it would be 100 times 250, this divided by 100 plus 250. So if you calculated that out, it would give you, I don't have a calculator right now, 100 times 250 is 25,000. And then if you divide that by 350, which is the sum, 250 plus 100, you would get 71.42. So that means that in this situation right here, where I have this first red circle, the sum or the total resistance for this parallel circuit is 71.4. And again, I found that out by using the equation that we talked about at the beginning, R1 times R2 divided by R1 plus R2. You do the same thing for here. So you do 200 times 350 divided by 200 plus 350. So 200 times 350 is 70,000. And then we would divide that by 550, which again is just a sum. So that is 127. So now we know that this first one here, I'm going to write it up here. So the 100 ohm, the 250 ohm part of our combination circuit, we know that the total resistance is 71.4, and that was basically the sum of both of those. And then we know that the second one here was 127. We also know by looking at our equation that we talked about at the beginning, now we can just add this together like it's a series circuit. So the sum of this is going to be the answer for the question of the total resistance of this whole circuit. So the total resistance of this circuit is 1 plus 127. And I'll let you do the math there. So at least I didn't give you the full answer. But again, just to kind of, I'll leave this up for a minute, but to kind of run through what I did. I didn't draw the equivalent circuit in this situation, but you could have. So the equivalent circuit in this situation would have just had two resistors. The first one would have been 71.4 ohms, and the second one would have been 125.4 ohms. And the way that I did that again was by first finding the situations in the combination circuit that are a parallel representation here and here, because this is where again the electrons split off. Using our equation, R1 times R2 divided by R1 plus R2 to find the sum here and the sum here, and then we can treat it as a series circuit. So I just simplified this by not doing the equivalent circuit and drawing that whole thing out. So if you want to draw it, that makes it easier, you can, but you don't have to. So yeah, so basically that is all I have for this week. I know a couple of you just got on, so if you're having troubles for this week, I can kind of go over what I just did and redo this, or if you want specific question answered, I can do that too. So but yeah, that's really all I have for today. I'm gonna exit out this one, and then I'll kind of go back to what I talked about. Maybe pull up the presentation I went over. But John, if you're good, I know you probably saw the beginning part already. So if you want to head out, you're good. I'll probably just repeat some of the areas that I already talked about. So. Okay. So, Mitch and Joe, I see you both got on relatively recently. Are there any questions that you want me to specifically go over, or do you want me to just, this was kind of a short lecture, but I basically talked about rheostats and potentiometers. If you want me to start from the beginning, I can, unless you have specific questions you want me to answer.
Well, I don't really have any questions, Mitch.
I'm sorry, I didn't hear you.
I don't really have any questions.
Oh, okay. If you don't have any questions, I do you want me to redo it, or I can restart this thing and re-explain it, or if you're good for this week, you're free to head out. You don't have to stay if you don't have questions.
Yeah, I'm good.
You're good? Okay. If there's anything that's confusing with this week, it's pretty difficult with the combination circuits. So just send me an email. I'd be happy to Zoom any day that you need me to. So
Okay, sounds good.
yeah, of course.
Okay.
Mitch, is there anything for you want me to recover from this lecture? So I talked about what a rheostat was. I talked again about these equivalent resistors and in series and parallel. I talked about this equation and how this R1 times R2 over R1 plus R2 is the same equation as here that we talked about last week. It's just a different way to write it. And then I did an example. I don't know if you caught this example here of basically a situation like this is exactly what you saw in the YouTube videos this week. And
Okay.
this, I'm sorry?
So,
Can you type in the chat? I can't hear you that well. I just want to make sure I answer your question. I'll leave this up so you can look at it. I guess I'll just, oh, okay, okay, let's see. Okay, I'm gonna go over this one, the one that's the screen's on right now.
yeah.
Perfect. Okay, sorry, I just want to make sure I talked about the thing you wanted me to talk about. Okay, so this exact problem was done in one of the YouTube videos, but it's only like, it's relatively quick, so that's kind of why I redrew it. So basically this week we're talking about combination circuits, and a combination circuit is one that has both series and parallel elements to it. This right here, if you ignore this bottom half, ignore this for right now, I'll talk about it in a minute, ignore all this, just look at this. This is an example of a combination circuit. The reason this is an example of a combination circuit is because we have series components, which is this right here. This is a series circuit, and then we have parallel components right here. If you remember from a couple weeks ago, a parallel circuit is one that your electrons at some point are going different directions. These two gray dots right here that I have are examples of the parallel components of this circuit. And that's because the electrons, which again, current is just electrons flowing through a circuit, our electrons are going across this arrow, all the same direction. So this right here is a series circuit. And then once they get to this node or junction, it's called, some of the electrons are splitting up this way and some of them are splitting up this way. So this right here is where we have a parallel element. And when the electrons get here, they add together and then they only follow this line. So these two junctions are situations where we have electrons splitting up, because right here they split up, and then right here they come back together because the electrons coming this way and the electrons going this way add together, and now we're going the same direction. So all of this is a series part of the circuit. This situation and this situation are the situations where we have the parallel elements. This is calculate both situations. So in this situation, whenever you're having a problem like this, so for this week, you're gonna be given figures that look like this or like this, and you're typically going to wanna always solve for the total voltage, total resistance, total current, your junction current, and your voltage drop. So if you kind of wanna write those on the side and then fill them in as you get them. So the first one, the total voltage, is easy to solve because the total voltage you're always given, it's just 10 volts. They give you this in the problem. They give you this right here is 24 volts. They give you it right here, 5 volts. They're typically always going to give you that. What's difficult to calculate is the total resistance, the total current, and these 4 elements. And that's because you have to take into consideration that you have both a series circuit and a parallel circuit. So how you solve these problems is you first want to transform your parallel circuit into a series circuit. Or basically you're going to sum these resistors up in order to get one number, and that one number we can then treat as a series circuit. So what I mean by this is that in this situation where we have the parallel resistors, right, because we have the junctions going this way and the junction going this way, we need to calculate the total resistance just for this situation. Looking at this, we can use this equation, the total resistance, this equation, R1 times R2 divided by R1 plus R2. That's exactly what was done in the YouTube video. So he did 10 times 10 divided by 10 plus 10 because he's calculating the total resistance for this parallel part. 10 from here, 10 from here, divided by 10 plus 10. So when you calculate the math out there, it gives you 5 amps. What he did right here in the YouTube video was he drew something called an equivalent circuit. So an equivalent circuit is basically what happens when you take your combination circuit here and then make just the parallel portion of your combination circuit a series, so then you only are left with a series circuit. So when they calculated the total resistance of 5 ohms here, now we only have 1 ohm, so we're not doing 2 anymore. So they rewrote this problem. So now we have 10 volts, again, same thing. 10 ohms comes from this 10 ohms right here in the series part of the circuit. This 5 ohms comes from the fact that we simplified this basically, and we found that the total resistance for the parallel portion was only 5 ohms. Now we can solve this just like we solved like the first 2 weeks of class, the easy problems. And that is using this equation. Series is just the sum of the resistors. And if you look, this is what a series circuit looks like, and this is exactly what this looks like now. So 10 plus 5 is 15 ohms. So that's as simple as how it is. So basically they were able to find the total resistance of this combination circuit by first finding the total resistance of just the parallel portion, then creating an equivalent circuit again and doing it that way. So basically that's the main component of this week. Sometimes you might have a couple different parallel circuits you'll have to deal with, but it's always going to be the same steps. So you're always going to just be basically simplifying the parallel portions into one number. So then you could just treat them as series and add them together. Once you get the RT was 15, the rest of the problem is easy because we can just follow Ohm's law, which is just V equals I times R to solve for the total current, because now we have the total voltage and we have the total resistance. So in order to calculate the total current, it's just V divided by R, 10 divided by 15, which is how they got 0.667. So basically that's how this problem was solved. The only other thing to note here that can be kind of confusing is that junction currents and voltage drops you can also calculate. So the voltage drops are situations where you might have your voltage change in parallel in different parts of this parallel circuit. Junction currents are situations right here and right here. So when our electrons are going here and they stop, right? Some of them are going to go this way and some of them are going this way. We talked about that last week, but we also talked about how the current splits up. So if we have 5 amps going in here, we might have 3 going this way and 2 going this way. And that's because when they add back up, we have 3 plus 2 to get 5 again. So anytime you have a junction, your currents are going to split up and then they're going to sum back together at the second junction so they equal where they were before the junction. So basically, that's what we're calculating. So we're calculating the junction currents means we're calculating the current right here or right here. And the way that we do that is by looking at this. So if we did, if you're calculating the junction current, you could still use Ohm's law, V equals I times R, or if we're solving for I, be V over R equals I. But in this situation, our R might only be 5 for the situation where, actually it would be, sorry, I just want to make sure I get this right. So I'll do the voltage drop first. I think that's easier to talk about. So that's 6.667 or 6.66 volts. So the way that they calculated that was by, we know that the total current is 0.6667, right? Because it says it right here, and we calculated it by doing 10 over 15. But if we only wanted the voltage drop or the voltage at the 10 ohm resistor right here, we only want to consider the 10 resistance. So we would do 0.66 times 10, and that's what gives us 6.66. And the reason we did 0.66 times 10 is 0.66 is our total current, and our 10 is our resistance at the 10 ohm, which is 10. So basically, in order to calculate voltage drops in a specific equation, you still use the equation I, which is current, times resistance equals voltage. It's still the same equation, but in the situation where you want voltage drop and not total voltage, your total resistance is just the only resistance that you're finding the voltage drop for. So you could also find the voltage drop at the 5 ohm resistors, which we know are these situations right here, by just doing 0.667 times 5, which is 3.33. So that's how the voltage drop is 6.67 here, and the voltage drop is 3.3 here and 3.3 here, which makes sense because the total volts is 10 and 6.67 and 3.3. If we treated just this as a series circuit, 6.67, 3.3 equals 10, basically. So that's kind of how it all relates together. So these are the things you're going to have to solve for: voltage, resistance, current, all of those, total current, total voltage, total resistance, and voltage drops and junction currents, which you calculate by, whatever junction or whatever voltage drop you're trying to find at whatever resistance, using that resistance value in Ohm's law, which is just V equals I times R. So that's kind of the equation or the problem that I solved for this week. Basically, same situation for the quiz. You're going to be asked to look at these two situations and determine the total voltage, total resistance, total current. And then you're also going to be asked about parallel and series circuits. So that's kind of what I was talking about when you both hopped on. And it's the fact that in this situation, you have multiple different resistors in the circuit. But some of them you can treat as a series, and some of them you can treat as a parallel, and knowing the difference is important. So in this first example here, we have two situations in the circuit where we have parallel resistors or parallel parts right here. And that's because at this point in the circuit, we're going to have electrons splitting off this way and electrons splitting off this way, right? Then they're going to meet back up here, and then they're splitting off again here, and they're splitting off again here. Then the rest of this is all a series circuit. So this is another combination. So a question might say, is R3 and R4 a series or parallel resistor? The answer is it's a parallel, right? Because in this situation, just looking at this, we have electrons going this way, and we have electrons going this way. On the contrary, on this situation, this R2 and R3 is an example of a series component or a series resistor in the circuit. And that's because in this example, the electrons going here down this pathway, they're never splitting up. So they're never doing a different direction, because a parallel circuit or parallel circuit is when we have electrons going different ways, like they are here, this way and this way. This situation, our electrons only going down this way are going one way. So this is a situation where we have a series resistor. If they were to ask you, is R2 and an R4 a series or parallel situation? Now this is a parallel situation because at this junction, we have electrons going this way and we have electrons going this way. So basically that's a question that you'll be asked for. So it's understanding that difference is huge. And then understanding in the situations where you do have parallel situations, like right here, R5 and R6, you're going to have to use this exact concept that we use here by finding the total resistance for the parallel and then summing it together and treating it as a series. So that's basically all you have to do for this week. Your quizzes are centered around those two problems. But, like for this one, just so just a quick synopsis, I don't know if you caught it when I did it, but I basically solved this for you, and it was easy. It was using this equation at the beginning, R1 times R2 divided by R1 plus R2. Using that equation to first calculate what the total resistance is for this component, then calculate the total resistance for this component, and then we're left with two numbers. Then you can add those together to get your total resistance, and then easily solve the current by just doing V equals IR, and then solving for current. So, yeah, I know it's pretty challenging, but hopefully this helped. If you have any questions after that, let me know. But that's really all I went over for this week, because I think, it's just the same situation for both of these, just different scenarios. In this scenario, you just have to add two numbers. You don't have to worry, like in this situation, about where you have this R6 and R7, you don't have to worry about, like doing that whole parallel R1 times R2, and that's because this is a series situation. You can just add them together. This is a series situation, just add them together. So you only have to, treat it, the parallels as situations where we have to find the. Okay, well, that's all I have. Any questions on any of that? You want me to explain anything?
No, I understand it, I think.
Okay, that's good.
Yeah.
Hopefully that helped. I know it's gonna be kind of confusing, but if you start to do the quiz and maybe there's a question or two you don't understand, let me know and I'd be more than happy to help you.
Okay, thank you.
Yeah, of course. Thanks for coming. Feel free to head out whenever, unless you have other questions.
Okay, bye.
Thanks. Bye. Joe, any questions for you? Hopefully that was somewhat helpful. I know this week can be kind of challenging.
Okay, I'm good.
You're good? Okay, hopefully that helped.
Yeah, I did. Thank you.
Yeah, just send me an email if anything's confusing. I'd be happy to help out.